Hello, friends. Welcome to this edition of Multiverse. You're watching Akulmach Business Channel. My name is Chandrakant. We have been seeing so many discoveries in space, in astronomy, and every day there are new things coming up. But today, I would like to talk about how do you calculate the mass of the celestial bodies and like sun, stars, whatever we see. How do we calculate sitting on Earth that this body will be so heavy or the mass of this body will be that much, etc. And we also talk about various black holes, very large object, and we say that these black holes are millions of times the mass of sun. How do we come to know about these things? Well, I will tell you one of the methods in which you can compute the mass of the black hole. There are several methods, but I will talk about only one of them. But I will also give reference to other methods which are used by scientists. So let us start our journey in calculating the mass of a black hole. Well, friends, before we start, I would like to mention three scientists and rather the theories proposed by these scientists. First being the Newton. And if you know that Newton's second law, which is force of any object is equal to mass into acceleration. And that is the amount of force that is applied. This is the second law of Newton. All of us, I would say almost 100% of the people who have gone to school have studied this formula in school. It describes how objects move around, and in fact the same formula, the second law of Newton, law of motion, was extended by Newton himself, and he came up with the law of gravity. I will explain that in a bit. But any object, whether it is a small object rolling down, small ball rolling down in front of you, or a large planet, can be explained the amount of force which is required to move the planet around the sun. So that is how the Newton was able to come up with a variation of his famous formula, which is F equal to ma, and he came up with this formula, which is called force equal to gravitational constant, mass of one object, mass of another object divided by the distance between them. So this is the extension of the same second law of motion by Newton, and I would like to ensure that we understand this basic law, which is almost like 500 years old, and keep that in mind before we move forward to the second formula, which is used in coming up with the mass calculation of the celestial bodies. So let's go to the second entity here, and the name of this great scientist is called Pythagoras. He was a Greek scholar almost 2000 years back, and he was fascinated by triangles or the pyramid structures. So he gave a lot of these theories and formulas which we know as Pythagoras Theorem, and we all study in our schools today. And the equation is very simple. That means if you are looking at a right angle triangle, then you know the length and breadth of the two smaller sides. You square them, that means A and B. You square A and add it to B square. That will be the length of the square of the longer side, which is opposite the right angle, which is called hypotenuse. So this way, by knowing the two parameters, you can come up with a third one. So this is a very basic equation given by Pythagoras almost 2000 years back, and it has been used in various, it has a very profound impact on the human society. How do we construct buildings? How do we construct our houses? How do we divide the fields? Using this equation has been used, and how do we compute areas of various non equal plots of fields? So using these Pythagoras, we can come up with various permutation combination, and I think at this point in time, I would like you to remember Pythagoras theorem and keep that in mind. Let's move to the third scientist, who existed during the uh, 20th century, more so during the First World War, where he came up with the famous equation called the Schwarzschild matrix. Karl Schwarzschild was a Jew born in Germany, and he was basically, contemporary of the great Einstein. And in order to come up with the, various mathematical formula around the general theory of relativity, he was actually analyzing the general theory of relativity, which was written by Einstein. And at the same time, the war broke out, the First World War. And in those days, most of the soldiers were stuck and used to fight from the trenches. And they had to use the cannons to destroy the enemy trenches. So in order to basically calculate the trajectory, how you can aim the cannon, but otherwise, there is no mechanism to aim the cannon. It is like a loose cannon. So Karl Schwarzschild, he was the director of one of the great institute in Germany at the time of the war, and he dedicated himself to this cause, and he actually participated actively in the war against the Allies. And during that, one of these conquests, both on the Eastern Front as well as on the Western Front, he came up with laws of controlling the cannonballs. And he described that, because cannonball usually takes a path of a parabola, so he came up with the equation of calculating the cannonball path, and based on his equations, now the soldiers can change the angle of elevation of their cannons to basically aim the cannonball at the right location. And this formula is used everywhere in the by every soldier today. Interestingly, while calculating this, Schwarzschild also realized that if there is a powerful enough cannon and which can throw the ball at a very high speed, eventually it will also escape the Earth's gravity. And there are various combinations. I mean, you can, using the Schwarzschild equation, you can attain a circular orbit which is constant falling. That means the cannonball reaches the orbit and then start to fall, but it will continue to fall because it will not reach Earth. It will continue. So this is the orbital velocity of the object. Or if you want to escape the gravity of the Earth, you have to again use the Schwarzschild equation and understand that how you can actually fire the rocket at a speed which will allow rocket to escape the gravity of the Earth. So using these three equations, we can come up with various mass equations for various objects like sun and different stars. Because when you look at the stars, they are so small, they are so tiny, and how do you basically measure the distance and also measure the mass? So using these mathematical formulas, which are very simple, these are all equations are 1 inch or even 1 centimeter long. So using these mathematical equations, sitting on Earth, just by observing, you can calculate the mass of various objects. And let me tell you that calculating the mass of the black hole is the easiest one. Calculating mass of a different star may be a difficult proposition, but to calculate mass of the black hole is easiest one. Why I'm saying this? Because when we calculate the mass of the black hole, there are certain infinities involved there, and the infinities are basically things like even light cannot escape. That means the speed at which you fall into the black hole is faster than the speed of light. That means it violates the laws of general relativity. So we know that the radius and beyond this size of the black hole, we will not be able to see even light escaping. So we call that as an event horizon. That means at the event horizon, the radius will be equal to the speed of light. I mean, the radius can be determined by the speed of light, which is the escape velocity of the black hole. So some of the parameters can be computed even before you start the observation. And The other parameters which I want to show you today, let me show you my whiteboard here. What I'm trying to demonstrate to you here is that if this is the black hole and this is the diameter of the black hole, we know that because we can compute based on the escape velocity of the black hole, which is equal to the speed of light. And based on that, we can come up with the radius of the event horizon. So each black hole will have a different event horizon. However, to look at this from Earth, we will be basically looking at using our telescopes, and we will know that outside the event horizon there is an accretion disk which we can see, and we can actually put that as part of our observations. So when we look at the diameter, we know exactly it casts as sort of a triangle. As you can see here, what I'm trying to show you is that it casted sort of a triangle, even though the angle here may be very, very small, but this angle can be, we will have some certain value. It can be very, very small, but it will have certain value. So based on this angle, we can come up with, we know this part already, the radius of the or the diameter of the event horizon. We know we can divide that by 2 and we will come up with a radius. So we know exactly that at the center point, at the radius, our line of vision, which is this line, is going to cast a 90-degree angle. So all we have to do is basically looking at the other end, which is the hypotenuse. Based on the angle, we can come up with this value of the hypotenuse. So we will actually make several observations of the black hole and create these calculations on both sides and come up with a mean to get the values which are required by us in terms of coming up with these formula, which will then eventually help us calculate the mass of the black hole. So now we have got the observation results, we have got the distance, we have got the angle, we have got the value of the hypotenuse, which is these lines which are on the external, and we also know the value of the radius. Just based on these values, we can compute the mass of the black hole. So let's do that, and let me remove my whiteboard. So now we see this is how the black hole will look like when we look at the black hole. And what I was trying to tell you some time back is that based on this way of observation, we can come up with various observed quantities of different elements. And then we can do a lot of observation maybe for a year, because Earth will also go around Sun. So at different locations during the year, we can actually calculate these values and come up with a mean value and apply that into this formula, which is the 2gm divided by light, the square of speed of light. So this radius will be called the Schwarzschild radius, and gravitational constant is a gravitational constant which is constant across the universe. And so multiply the radius twice of the gravitational constant and divide by the speed of light will give you the mass of a black hole. And this is the method by which we can calculate the mass of any object in space. And however, because of the black hole, because of the Schwarzschild equation, we can easily compute the radius of a black hole. It is very simple to ascertain the mass of a black hole, which we see just on the basis of observation. So this is something which I thought I will talk about. Simple, very simple equation, how we can calculate the mass and distance of these celestial bodies, and also calculate sitting on Earth. These objects are so far off. Sitting on Earth, we can calculate the mass and various other properties of a black hole. Now, I'm not talking about other complicated issues here, because what if the black hole is spinning? What if the black hole is charged? Then these same equations will be used to calculate these parameters, and those charge and spin will also be incorporated in this, and then you can actually come up with a near accurate estimate of the mass of a black hole. So friends, I wanted to share this method of calculating the mass of the celestial bodies using three simple equations sitting on Earth on the basis of observation. I like to know your comments, and as always, thanks for watching, and I will catch you again in the next video, my friend.